Hi there, settle in and rest your shoulders. Let the chair hold you. Let your breath fall into a slow, easy tide and feel the day loosen its grip. You are safe here. Tonight, we'll drift toward a small, bright rumor in the dark, a distant world that some whisper might carry a 99% chance of life. Not a trumpet, not a headline, just a gentle possibility, a candle seen across a wide, starry field. The James Webb telescope has given us hints, patterns of light and shadow that suggest air to breathe, seas to dream about, and the quiet work of something living. As we float through these signs, we'll move slowly so your mind can wander while your body rests. If this calm company helps you unwind, feel free to like and subscribe so more sleepy travelers can find their way here. For now, close your eyes a little more and let the cosmos dim the room. Let's begin. Under the quiet stretch of Leo's constellation, light has been traveling toward us for more than 100 years, tiny ripples of brightness crossing the dark until they finally reach the mirror of a telescope, waiting in silence. There, among those threads of starlight, was a pattern so delicate it almost seemed accidental, but it wasn't. The James Webb Space Telescope had captured the breath of a distant world, a planet circling a red dwarf sun, its air trembling with signs that something might be alive. Imagine a world bathed in gentle crimson light, the warmth steady, neither scorching nor cold, around 120 degrees Fahrenheit, enough for oceans to glimmer and clouds to form. Its name, K218b, sounds more like a code than a home, but perhaps that is how all discoveries begin. Numbers first, meaning later. When the data arrived on Earth, terabytes of infrared whispers, scientists watched it unfold like a heartbeat on a screen. Among the gases drifting in that alien sky, one stood out: dimethyl sulfide. On our own planet, that molecule is born only from living things. Phytoplankton in the sea, tiny invisible gardeners of the air, make it as they breathe. And here it was again, impossibly far away, glowing faintly in the light of another sun. At Cambridge, Niku Madhusudan leaned closer to the data, his breath almost still. The odds that it was a mistake were nearly non-existent, less than 3 in 1,000. His fingers trembled, not from doubt, but from the weight of what that number meant. If the readings were real, then life had announced itself across 120 light years of emptiness, not through words or signals, but through chemistry, the universal language of existence. K218b orbits gently in its star's habitable zone, the golden distance where water can remain liquid. It's larger than Earth, about 8 times more massive, its gravity pressing firmly but evenly, like the hand of a steady giant. Wrapped in a thick robe of hydrogen, it holds its heat like a cradle, spreading warmth from its bright side to its dark. The night there is never truly cold. Even the places that never see sunrise stay tenderly warm beneath their long shadowed skies. Scientists once thought worlds like this were too strange to hold life, too heavy, too gaseous, too far from our comfortable model of Earth-like. But this planet whispered otherwise. The hydrogen, once dismissed as hostile, turned out to be a perfect blanket, keeping the oceans below from freezing, keeping the winds soft and steady. Methane and carbon dioxide danced together in its sky, and in between them, that same rare molecule, dimethyl sulfide, rose like a fragile signal fire. It was not proof beyond all doubt, but it was a hint strong enough to make the world hold its breath. The numbers spoke softly, but clearly 99.7% certainty that what they were seeing was real. In science, that kind of confidence is almost sacred. Yet it was not just about the molecule. It was about the story it told, that life could bloom under colors we once thought impossible, in air too thick for our lungs, under a sun that glows red instead of gold. K218b belongs to a class of planets called super-Earths. Bigger than ours, smaller than Neptune, they had long been filed away as curiosities, worlds with too much gravity, too much atmosphere, too little chance. But when Webb's mirror looked closer, the old assumptions began to melt. The idea that only Earth-like planets could nurture life started to feel narrow, almost childish, like believing flowers can only grow in one kind of soil. If you were to stand on the edge of K218b's ocean, if such a place exists, you might feel 3 times your normal weight. Your knees would ache a little under the pull. Your heart would beat slower, deeper. But you would also be standing beneath skies that never freeze, where stars shimmer through hydrogen clouds and the sea never stops steaming gently into the air. The weight might feel grounding, not crushing. The kind of gravity that keeps everything close, that holds oceans in place for millions of years without letting them slip away. Mars once had air and water too, until its weaker gravity let both drift off into space. K218b is no such fragile world. Its heavy pull keeps its blanket of gases tight around it, making it stable, almost eternal, compared to our restless Earth. And its star, a red dwarf, burns with a slow patience. Our own sun will swell and die within a few billion years, but a red dwarf can glow for trillions, a steady lamp in the endless dark. Life there would have time to change, time to grow, time to imagine itself into complexity beyond anything we know. What stirs the imagination most is not the heat or the chemistry, but the absence of certain things. There is no ammonia in the atmosphere, none of the harsh fingerprints of a sterile world. Instead, there's a balance that suggests something is breathing, taking in, letting out, shaping the air. On Earth, life and air are partners in a quiet dance. Forests inhale carbon dioxide and exhale oxygen. Oceans trade methane and sulfur compounds with the sky. To see a similar rhythm light years away is to glimpse the choreography of existence written anew. The more the data was studied, the more it seemed this planet wasn't a barren gas giant, but a place where the boundary between sea and sky might shimmer, where sunlight filters through hydrogen mist to touch water below. Perhaps, beneath that heavy atmosphere, there are currents, slow, rich, teeming with organisms that drift as softly as our plankton do, each one part of a great invisible web. The idea is almost unbearable in its beauty, that somewhere beyond the reach of every radio signal, something small is alive, unknowing of us, yet connected by chemistry and starlight. Life, after all, is a stubborn thing. It rises wherever conditions allow, reshaping its home to suit its rhythm. And on K218b, the air itself seems to echo that rhythm. If this finding holds true, it changes more than astronomy. It changes solitude. The feeling of being alone in the cosmic dark begins to fade, replaced by the possibility that the night sky is full of neighbors we cannot yet see. The discovery humbles and comforts at once. We may not be the only dreamers under starlight. Red dwarfs like K20-18 are the most common kind of star, 3/4 of the galaxy's shining hearts. If even a fraction of their planets hold life, then the universe is not silent at all. It's a chorus, faint and vast, waiting to be heard. Perhaps our search for Earth's twin was misguided from the start. Maybe the universe prefers variation over repetition. Maybe it grows its gardens under red suns, in seas that smell of sulfur and salt, on worlds where gravity feels like an embrace. Somewhere tonight, the light from K218b is still traveling toward us, carrying the signature of that strange sky. By the time it reaches your eyes, if ever, it will be centuries older, yet still fresh enough to whisper the same quiet truth. Life does not need to be like us to be alive. It only needs warmth, patience, and time. And the cosmos, it seems, has plenty to offer. Far from city glow and hurried clocks, a gold mirror waits in a cold so deep it has no wind. The James Webb Space Telescope keeps vigil there, 1,000,000 miles from our warmth, balanced at a quiet gravitational saddle called L2, where Sun and Earth tug just enough to make a stable perch. Its face is all facets, 18 hexagons trimmed in the thinnest breath of gold, opening like a metal flower that never wilts. Behind it, a sun shield the size of a tennis court stack stretches out like layered moonlight, 5 thin sails that keep heat at bay so instruments can dream in darkness. Colder than the plains of Pluto, cold enough that faint heat from ancient things becomes visible. Infrared is the light of embers and breath, of warm seas and dust between stars, light our eyes can't see, but our skin would recognize if it could read. In that spectrum, a planet is not just a tiny occulting dot, it is a voice. When the world we've been following slips across the face of its red star, a trace of starlight filters through the planet's air and reaches us changed. Certain wavelengths go missing, sipped away by molecules. Water leaves its curve, methane its delicate bite, carbon dioxide its measured dip. Taken together, these curves become a signature, like a slow pulse on paper, like tide marks on a shore no human has ever walked. Webb reads those marks with a steadiness that feels almost uncanny. The mirror is 21 feet wide, nearly triple Hubble's, but size is only part of the story. Each segment can tilt by less than the width of a human hair, then tilt again and again, until all 18 behave like a single surface. The alignment is so true that people sometimes say, with a little smile, it could sense the warmth of a bumblebee on the moon. It's an image more than a measurement, but it captures the idea, sensitivity to whispers while the universe roars. The roar here is the star. A distant dwarf outshines its companion planet by billions of times, the way a searchlight drowns a candle. To hear the candle, Webb doesn't simply block the beam and reveal the glow. During these transits, it does something subtler. It watches the star with exquisite patience, collects spectra in long, careful sequences, and then the data are cleaned of jitters and flares and instrument murmurs, the way an audio engineer removes a hum without touching the music. Algorithms and human judgment work together, detrending, modeling, cross-checking, until the signal left behind looks less like noise and more like chemistry. The effect is like standing near a jet engine and learning to hear a whisper at your shoulder. You begin by subtracting what is deafening, and what remains, if it remains, is a voice. The possibility that dimethyl sulfide is in that voice asks us to listen with care. On Earth, that molecule is woven into the life of the oceans, released by tiny living things and carried into the air, where it helps seed clouds that cool the sea, that feeds the life, that releases the molecule again. A loop, small and grand at once. Seeing the same spectral fingerprints far away would be astonishing, which is why the instrument team and many others check and recheck each photon, compare models, test different assumptions about clouds, hazes, star spots, calibration. Months go by. The telescope watches again. The pattern still glints. Maybe, almost, enough to steady a scientist's breath while still welcoming healthy doubt. In science, the word almost is not a failure. It is a promise to keep looking. Temperature drifts up through this same kind of inference, not a thermometer dipped into alien water, but a reading of how much energy has been taken in and given back, of how the air layers glow, of how molecules move at different heats. What emerges for this planet is a warmth that feels oddly familiar, close to the heat of a desert afternoon, to a hot bath that someone forgot to turn down. Numbers are tempting in their neatness, yet even a number that seems exact carries a fog of uncertainty when measured across interstellar distance. What matters most in the quiet of this night is the shape of the truth. The world is warm enough for water to remain liquid and not so hot that it all flees into steam. Habitability begins there, in the temperate cradle between frost and boil. A hydrogen-rich atmosphere plays the role of blanket and messenger. Hydrogen is light, but when there is enough of it and gravity is strong enough to hold it close, it becomes a faithful keeper of heat. Day and night begin to share their temperatures like neighbors trading stories across a fence. On a planet likely locked to its star with one hemisphere facing perpetual dawn and the other swaddled in endless midnight, the blanket smooths the extremes. Winds move energy around. The night side does not bite. The day side does not scorch beyond remedy. Where Earth's thin air allows drama blizzards and heat domes, polar deserts, and tropical forests, this world may favor consistency, the sort of global mildness that lets life spend itself on growth rather than defense. There is a quiet wonder in imagining a biosphere built in such steadiness. Here, winters do not empty larders. Summers do not burn harvests to ash. Life might not need to migrate, hoard, hibernate. Energy that on Earth is spent on survival could flow into intricacy, into longer lives, into patience. Perhaps the seas beneath those hydrogen skies move with slow currents, dense and nutrient-rich, where small organisms rise and fall on tides that are more chemical than lunar. With time unspooling generously from a red dwarf that may burn for trillions of years, evolution would have the one resource it covets most: duration. Back at L2, the instruments that made these inferences remain colder than we can easily imagine. One camera and spectrograph watches in the near infrared where warmer molecules speak. Another, chilled with special pumps and plumbing until it is barely above absolute zero, listens deeper into the mid-infrared where dust and more complex chemistry glow. Every measurement is a compromise between exposure, time, and stability, between the star's moods and the instruments. So, observations repeat, stack, and build confidence, layer by layer like thin sheets of leafing gold, where a single transit is a glimpse, a season of transits is a portrait. All of this depends on an orchestra of careful subtractions. Starlight must be separated from planet light. Instrument quirks must be split away from celestial truth. Patterns caused by star spots, cool bruises on the stellar surface, must be distinguished from the breath of alien air. The math behind these separations is not a cold engine, but a craft, iterative and watchful, helped along by machine learning that can sift millions of possibilities more quickly than we can, and restrained by human caution that asks the right skeptical questions When the final curve emerges, dip here for water, dip there for methane, a subtle bend that could be carbon dioxide, a hint of something rarer. What we are really looking at is the residue of subtraction, a voice revealed by removing everything that is not the voice. The same approach allows a kind of temperature map, not a picture as our eyes would know it, but a climate line drawn from the balance between incoming and outgoing energy. The planet's warmth becomes not a single number carved in stone, but a range with a center that feels like a hand held comfortably close to a hearth. In that range, molecules keep their shapes. Proteins, if they exist there in any form, would be less likely to unravel. Membranes could stay supple. Chemistry could proceed with eagerness rather than haste or torpor. Laboratory work here at home has shown how stubbornly life tolerates heat, how certain microbes thrive in hot springs or hydrothermal vents. And though those temperatures far exceed what is cozy to us, the lesson holds. Warmth within a forgiving band widens life's playground. If the planet really keeps such evenness from bright side to dark, from equator to pole, the implication is profound. On Earth, variation drives diversity, but it also drives stress. Here, the stress would ease. Evolution might explore different axes, not adaptations to seasons, but to pressure and chemistry, not migrations, but depths, not survival in scarcity, but competition in plenty. The thought is speculative. Of course, all of this is, but it is a working story that fits the lines we see. Through it all, Webb changes not only what we know, but how we feel about knowing. It teaches patience. Light that left a star before our grandparents were born is only now telling us how a far ocean might smell. It teaches humility. Our idea of Earth-like was a mirror held too close to our own faces. It teaches tenderness, that life, if it is there, announces itself not with shouts, but with small edits to an atmosphere, with absences and excesses a careful listener can hear. Some nights, the metaphor returns the bumblebee on the moon, and it feels less like hyperbole and more like a kind of prayer for sensitivity. To build a machine so exacting that it can detect warmth and breath across the void is to extend our own senses until they brush something intimate and unseen. If this is, as some have said, humanity's greatest eye, then what it sees best is not brightness, but balance. The precise middle, where water stays water, where air keeps secrets without hiding them, where time can stack complexity grain by grain until a world wakes up. The mirror at L2 will keep watching. Stars will dim and brighten on their own schedules. Planets will cut their quiet paths. Spectra will pile up in archives where future hands will find more meaning than we can squeeze from them tonight. Whether dimethyl sulfide proves as certain as it first seemed, whether another molecule takes its place in the story or adds a new verse, the essential drift does not change. Somewhere under a red sun, a planet wears a warm, steady coat and may keep seas that do not freeze. The universe, patient as ever, is letting us hear what warmth sounds like across impossible distance. Breathe with that thought. Let it move in and out, gentle as tide, as the telescope holds its gaze and the numbers settle into a picture of a world that could be comfortable, could be kind, could be busy with quiet work beneath a sky the color of sleep. Dimethyl sulfide, 3 small words carrying the hush of oceans. Say them slowly, and they sound like a tide slipping over sand. Dimethyl sulfide. On our world, This molecule rises from living seas. Tiny drifters, phytoplankton, make it as part of their daily work, releasing it into the air, where it helps weave clouds that soften sunlight and guide the rain. Bacteria tend the cycle, algae join the choir, even some plants add their notes. Dimethyl sulfide is less a chemical than a conversation between life and weather, a whisper traded between ocean and sky. When Webb found a hint of that whisper in the light from K218b, scientists felt the ground tilt beneath them. A faint pattern in the infrared looked as though this distant world might wear the same perfume our oceans do. On Earth, dimethyl sulfide is made only by life. The enzymes that build it are intricate, born of evolution's patience. No volcano, lightning strike, or mineral reaction has ever made it by accident. To see its spectral trace light years away was to glimpse a possibility both thrilling and fragile, that somewhere beneath a red sun, chemistry might be breathing. Still, honesty is part of wonder. No scientist calls a molecule proof. The universe is inventive. It finds side roads. So, dimethyl sulfide becomes not a verdict but a witness, a strong hint that invites careful doubt. Could unknown processes in alien air create it? Could hydrogen, carbon, and sulfur mingle in ways we haven't imagined? Maybe. Knowledge is a moving shoreline, and caution keeps us from mistaking every shimmer for land. That is why discoveries come wrapped in probabilities, not proclamations. In this case, the signal rose above noise with a confidence called 3 sigma, meaning only about a 3 in 1,000 chance it's random. Enough to listen closely, not enough to stop asking questions. Reaching even that level required patience, bordering on devotion. The signal was faint, just a few parts per billion of the starlight filtered through the planet's air. Webb had to measure wavelengths to 1 part in 10 million, then repeat the measurement again and again as the planet crossed its star. Months of data, millions of photons, and the same soft curve kept returning. Dimethyl sulfide's structure tells a quiet story. 1 sulfur atom clasped between 2 carbon-bearing wings. On Earth, enzymes shape those bonds with exquisite care. The molecule slips into the sulfur cycle that ties together water, air, and life, rising from seas, seeding clouds, cooling the very waters that birthed it. A feedback loop elegant enough to make weather part of metabolism itself. If such a loop existed on K218b, it would mean biology not as an exception, but as a natural rhythm. Chemistry's instinct for complexity repeating across space. The faint light that carries this story travels 120 years to reach us, bent and filtered until only a few of its wavelengths remain. During a transit, a fraction of the star's glow passes through the planet's atmosphere. Molecules there sip away specific colors, leaving tiny notches that scientists read like fingerprints. Extracting those prints is delicate work, subtracting starlight, correcting for the telescope's own breathing, taming the red dwarf's flares. What remains, if anything remains, is the planet's breath, recorded as light. A hydrogen-rich sky makes the task both easier and harder. Easier because hydrogen's lightness lifts the atmosphere high, giving molecules more room to leave their marks. Harder because hydrogen's broad absorption can blur the fine lines. Yet Webb's instruments are patient listeners. They collect more transits, compare wavelengths, let different teams check each pattern. The goal is not to declare victory, but to see whether the melody repeats. If it does, The implication is staggering. To change a planet's atmosphere, enough for life's byproducts to be seen across light years would require a biosphere, immense and active, a world-scale metabolism. Not a few microbes huddled in cracks, but oceans or continents thick with chemistry. The thought reshapes solitude itself. Earth would no longer be a single bright island of life, but one of many archipelagos scattered through the dark. And if the signal fades with more data, the lesson remains luminous. We have learned to listen this closely, to hold a mirror steady enough to catch the breath of another world, to measure heat with the tenderness of a fingertip, to let a planet's atmosphere speak in syllables of light. Even a mistaken scent teaches us how to sharpen our sense. Still, imagine if it holds. Then K218b's air would carry the same elemental alphabet that life here uses: carbon, hydrogen, oxygen, nitrogen, sulfur, written into new words, but spoken with familiar grammar. Such kinship across 120 light years would mean that life may not be a miracle, but a tendency, as natural as gravity, arising wherever conditions lean the right way. To grasp the scale of certainty, think of flipping a coin 1,000 times and watching it land the same way 997 times. That's roughly the odds that the dimethyl sulfide signal is real. In physics, that same threshold, 3 sigma, has confirmed particles, waves, and planetary discoveries alike. Yet even then, humility persists. Unknown chemistry, stellar spots, instrument quirks, each could mimic a molecule's trace. So teams test every alternative, blind their analyses, challenge their own code. Truth in science is not declared, it's endured. Whether the molecule survives scrutiny or not, Webb's achievement stands. The telescope can discern changes in light 1 part in 10 million, sense warmth from a world we can't see, and translate that warmth into a map of possibility. It shows that technology and patience together can make the invisible intimate. It proves that we can look across space not only with curiosity, but with care. If dimethyl sulfide truly fills that alien sky, then life there must be busy and abundant. Clouds could rise from living seas. Winds could carry scent over endless waves. Chemistry could be both creature and climate. Under a dim red sun that will shine for trillions of years, time itself would be generous enough for evolution to sculpt wonders. And if not, if the molecule dissolves under better data, then the search goes on, sharpened, wiser, and no less beautiful. Because what Webb has given us is not merely a possible answer, but a new kind of hearing. To detect a hint of life across the void is to realize that existence hums even in silence, that every photon is a messenger, and that truth, like light, travels patiently. Beneath the slow red glow of its distant star, K218b turns through a twilight that never ends. Below that sky lies an ocean, the color of smoked glass, so deep and heavy it could swallow continents whole. It is not made of water alone, but of water folded with hydrogen, fused by pressure into something between liquid and dream. Its surface would shimmer faintly like metal, its waves moving slowly under gravity 3 times our own. Down there, the boundary between sea and sky is blurred, a place where air dissolves into liquid and liquid breathes back into air. This strange ocean exists because K218b's atmosphere and surface are bound in constant exchange. Hydrogen from above sinks into the water, vapor rises to take its place. The mixture stays stable across impossible ranges of heat and pressure liquid, from near freezing to well above the boiling point of water on Earth. Within that range, chemistry can move freely. Molecules can meet and organize. Life, if it has begun, can thrive. Earth's deepest trenches crush even steel, yet on K218b, hydrogen softens pressure's hand. The ocean stays fluid and friendly, even at depths that would destroy a submarine. Hydrogen acts as a buffer, letting the planet keep its water without freezing or boiling it away. It also solves another riddle, the slow leaking of air into space. As hydrogen drifts upward and escapes, more seeps out of the ocean to replace it, creating a self-healing atmosphere that could last for trillions of years, long after our own world falls silent. Hydrogen is more than structure. It is food, breath, and fuel. On Earth, a few bacteria use it to live, but they are limited by its scarcity. On K218b, hydrogen is everywhere, so life could build entire metabolisms around it. Imagine organisms that breathe the ocean itself, drawing in hydrogen and exhaling other gases, shaping the air above without us ever knowing their names. The dimethyl sulfide detected by Webb might be only one verse in a much larger song, one note in a planetary choir built on alien chemistry. Such life might be invisible to us. Our telescopes search for oxygen, ozone, and carbon dioxide, but a hydrogen-based ecosystem would speak another language. Its signatures could hide in balance, its breath blending perfectly with the atmosphere's own. We might already be watching a living planet and not yet know how to recognize the pulse. Models suggest the ocean could stretch hundreds of miles down, far deeper than any on Earth. At the top, faint light might filter through crimson clouds. Deeper still, there would be darkness, rich with heat and chemistry. Perhaps layers of ecosystems move through that vast column, drifting colonies near the light, slow feeders in the twilight, heat-loving organisms near the bottom. In a world where seasons don't exist, life could flow in centuries-long cycles instead of years, evolving slowly but thoroughly until the ocean itself becomes one continuous living system. Such stability would give life what it rarely receives on Earth: time. With eons to unfold and almost no environmental stress, evolution could turn inward, growing complexity rather than speed. Organisms might merge, cooperate, or expand into forms beyond our categories, webs of chemistry spanning miles, exchanging signals through pressure, heat, or magnetism. A single idea life as network, not individual, might define the whole ocean. Above this deep calm, the atmosphere performs its own alchemy. Methane swirls through hydrogen clouds like veins of gold smoke. Methane here may be more than a byproduct. It could be a heartbeat of the carbon cycle, regulating heat and chemistry across the planet. On Earth, methane breaks down quickly. On K218b, something must be replenishing it. Perhaps volcanoes, perhaps life. Higher up, carbon dioxide and hydrogen join in strange dances, forming fleeting crystals that flash and dissolve. In certain layers, pressure grows high enough to turn carbon into diamonds, creating rain made of jewels that drift down and melt in the lower air. To us, it sounds like myth. To that world, it would be weather. Each gas serves the others. Methane traps warmth, hydrogen spreads it, carbon dioxide balances it. Together, They smooth the temperature from pole to pole, from endless day to endless night. Because the planet always shows one face to its star, heat would normally pile up on the day side and leave the far side frozen. But the dense atmosphere carries warmth like an ocean current, turning extremes into gentle gradients. Storms might stretch around the entire world, slow, looping spirals that mix the hemispheres until both glow at the same faint red. That same thickness shields the surface from harm. Red dwarfs are temperamental, prone to flares that could strip or sterilize thin atmospheres. Yet, K2-18b's hydrogen blanket catches those blasts and diffuses them harmlessly. Radiation that would scorch Earth instead becomes warmth, feeding the cycles below. Under that protection, life, if it began, would never need to hide underground or behind shells. It could flourish openly, in peace. The chemistry above mirrors the calm below, complexity without chaos. Carbon, hydrogen, oxygen, nitrogen, sulfur, familiar elements, but rearranged into symphonies our planet never composed. Photosynthesis, if it exists there, might use infrared light instead of yellow. Organisms might be dark red, copper, or nearly black, absorbing every faint photon. Instead of green forests, imagine oceans glowing softly, absorbing the star's warmth and re-emitting it as invisible heat. At mid-altitudes, where pressure is gentle, life might drift freely. Gas-filled membranes could float through the sky, feeding on airborne compounds, rising on warm currents, and falling through cooler layers. These creatures would never touch land, perhaps never even know it exists. Their migration between the bright and dark hemispheres could create a planetary rhythm, an atmosphere alive not just with weather, but with movement that thinks. Every molecule would take part in this endless cycle. Methane forms, breaks, and reforms. Carbon dioxide dissolves into the sea and returns to the air. Hydrogen escapes and is replaced. Even diamond rain may feed the deep ocean, returning carbon to the mantle to begin again. Nothing stands still. Everything circulates, as if the planet itself were a single living organism breathing through a million chemical lungs. We might see this as paradise, a self-healing, balanced world, but it is simply the universe being efficient. When energy, matter, and time align so smoothly, life becomes inevitable. It may not have eyes or leaves or bones. It may not need tools or fire. It may be content to exist, to flow, to persist. Consciousness, if it ever appears, could be collective. Awareness spread thin and wide, thinking not in pictures but in chemistry, feeling not moments but epochs. From our distance, all we can sense is the reflection of that serenity. Webb's golden mirror captures scattered photons, infrared whispers that tell of hydrogen, methane, water, carbon dioxide. Those signals travel 120 light years to become patterns on a screen, numbers in a file, a curve that hints at warmth, equilibrium, maybe breath. They are tiny things, yet together they form a picture, a planet not hostile, but hospitable in its own alien way. We once searched for another Earth. What we found instead is the idea that life does not need Earth at all. It can bloom in hydrogen seas, breathe methane air, and turn carbon into rain that sparkles as it falls. The cosmos does not copy. It improvises, inventing new versions of vitality wherever physics leaves space for it. So perhaps, under that crimson light, something small is stirring now. Maybe translucent shapes drift through the heavy water, or soft filaments ripple where day meets night. Their byproducts rise into the sky, shimmer in starlight, and cross the void to reach us. In those photons, we catch a glimpse not of aliens, but of continuity, the same urge that animated our oceans billions of years ago, written again in a new dialect. K218b's Hydrogen Sea may be the most welcoming cradle for life we have yet imagined, not because it resembles our home, but because it proves that home can take infinite forms. Life is not an accident of one planet's chemistry. It is what matter does when given patience. Far from the bright insistence of our sun, the small red star called K2-18 burns quietly, like an ember that never dies. Its light is gentle, tinted the color of rust and dawn, yet steady, so steady it could outlast everything we know. Where our sun blazes for a brief 10 billion years before swelling and consuming its children, K2-18 will burn for trillions. Its pulse will continue long after our own star fades, long after the last mountains on Earth have turned to dust. Red dwarfs like this one are the universe's patient hearts. 3 out of every 4 stars belong to their kind, small, cool, slow burning, and everywhere. Their restraint is their gift. Because they sip fuel instead of swallowing it, they live 1,000 times longer than stars like ours. Around them, time stretches like a calm sea. A planet that finds the right distance, the right chemistry, could bask in that glow for ages upon ages, long enough for life to rise, evolve, and settle into its own rhythm without fear of extinction by its sun. K2-18 is unusually well behaved for its class. Many red dwarfs flare with violence eruptions so fierce they can strip atmospheres bare, sterilize entire worlds. But K2-18 is quiet, serene, a cosmic hearth. Its flares are few and faint, its radiation softened by a steady breeze of light. It offers something rare in the cosmos: consistency. Energy not in bursts, but in gentle persistence. For life, consistency is everything. Orbiting close to that dim star, the planet K2-18b circles once every 33 Earth days. It hugs its sun so tightly that it would seem too near, yet because the star is cool, the planet receives almost exactly the same warmth that Earth does. In that perfect balancing act, the Goldilocks zone liquid water can exist, neither frozen nor boiled away. But unlike Earth, which will one day lose its ocean to the swelling of our dying sun, K2-18b may keep its seas for trillions of years, a home that doesn't expire. The planet is tidally locked, one face always turned toward its star, the other eternally dark. Yet, this is no curse. Its thick hydrogen atmosphere moves heat around with exquisite grace, turning harsh contrast into balance. On the bright side, light filters through crimson clouds. On the dark side, air and ocean glow faintly with the warmth carried from the day. Between the two lies a perpetual twilight, a ring of eternal dusk where winds are soft and the temperature holds steady, perhaps the most habitable place in the universe. Imagine standing there, if standing were possible, under a sky that never brightens and never fades, with the red sun hanging unmoving on the horizon. The air would be dense but kind, the ocean stretching outward, its far side lost in shadow. It is in places like this that life may flourish, where nothing ends too soon, where time itself is a steady companion. For beings that could evolve here, existence would unfold in slow abundance. On Earth, It took nearly 4 billion years for life to climb from single cells to forests and cities. Around a red dwarf, evolution has the gift of patience measured not in billions but trillions. Civilizations, if they arise, could span epochs we cannot imagine. When our species is long forgotten, when our own sun's ashes have cooled, the children of such worlds might still be writing their stories beneath a gentle red light. Yet the distance between us remains immense, 120 light years, a number that sounds abstract until you remember what it means. The light we see tonight left K218b when the early 1900s were still unfolding on Earth, when radio was young and airships still ruled the sky. That light traveled across the vacuum for more than a century before slipping into Webb's golden mirror, carrying within it a message written in molecules. Every photon that struck the telescope had touched the air of that world, had passed through clouds perhaps made by living breath. At that distance, even miracles arrive as whispers. The telescope must collect photons for hours to hear the faintest signal, to tease out the dim pattern of dimethyl sulfide or methane from the star's brilliance. Yet the weakness of the light is also a strength. It stretches our instruments to perfection, teaches us patience, and it lets us look backward in time. When we observe K218b, we see it not as it is now, but as it was a century ago. The molecules we detect today are the echo of an older world, a snapshot of alien weather, perhaps even the breath of creatures long since changed. That is the quiet paradox of astronomy. The farther we look, the further into the past we travel. We are not only finding another planet, we are discovering a history written in light. The biosignature Webb caught, that faint curve of possibility, was born before our own ancestors learned to split the atom. We are reading the century-old sigh of another biosphere. To detect life across such distance means that life there must be abundant. A few microbes could never change an atmosphere enough to be heard from here. Whatever produces dimethyl sulfide on K218b must exist in planetary numbers, in oceans, plains, or floating colonies that together alter the sky. This is not survival on the margins. It is a planet alive on a scale that rivals our own. And this world is close. In cosmic terms, the Milky Way holds hundreds of billions of stars. Shrink it to the size of North America, and K218b would be another grain of sand just a few towns away. Within this local patch of galaxy lie thousands of such systems, most orbiting red dwarfs, most waiting for their stories to be found. If life thrives on one, it likely thrives on many. The night sky may be far busier than it looks. Future telescopes will reach even further. The extremely large telescope, its mirror wider than a house is tall, will soon turn toward K218b. It will analyze its air molecule by molecule, perhaps finding not just dimethyl sulfide but other signs of metabolism, hydrogen imbalances, complex carbon chains, faint variations in color that mark weather shaped by biology. Each new observation will refine the portrait of this world, bringing the blur of distance into clearer focus. That distance, impossibly large for travel, becomes intimate in understanding. We cannot go there. We cannot send a probe across 2 million years of flight. Yet the light that left that world has found us, and that is enough to begin a conversation. The same laws of physics that carried their photons to us will carry ours back. Our first radio signals, broadcast a century ago, are just now washing over K218b's skies. If there are listeners there, if they too built instruments to read the invisible, they might be hearing the ghost of our own beginnings. Morse code, early jazz, the hum of human invention leaking into the dark. It's possible that two civilizations are now trading whispers across time, each receiving the other's past. To them, Earth is young and curious. To us, K218b is ancient and serene. In that exchange, the universe becomes smaller not because the distance has changed, but because the silence between stars has been broken by breath. K2-18 and its world remind us that life does not need bright suns or perfect planets. It needs only stability, time, and a bit of kindness from physics. Around these red dwarfs, the cosmos is offering that gift again and again. If we could look out across the galaxy, we might see countless embers glowing, each one a small, steady promise that life has more time than we ever dreamed. Perhaps somewhere in that dim red twilight, something stirs even now, a ripple in a hydrogen sea, a cluster of living chemistry aware in ways we can't imagine. And perhaps, without knowing it, it is already answering. The photons that left their sky are here now, finding their way into our instruments, our equations, our wonder. They tell us not just that another world exists, but that time itself has room for life to unfold endlessly. Picture a firefly hovering beside a searchlight, its tiny glow drowned in white blaze. Now, move that scene 1,000 miles away and try to take its portrait. That's the flavor of the problem. A planet's faint shimmer pressed up against its star's overwhelming glare. The trick, learned at home by studying our own sun, is to sculpt the light until the blaze steps aside and the whisper remains. Astronomers call the tool a coronagraph, an engineered eclipse. For decades, we've used it to veil the sun's face and reveal the delicate corona flowing around it. Webb's designers carried that craft to the realm of exoplanets, building masks and mirrors that don't just block light but shape it, coaxing the star's brilliance into patterns that cancel themselves while letting neighboring faintness slip through. It's not a single disk laid over a star. It's a choreography of apertures and phases, each piece tuned to cancel a different kind of glare. The tolerances border on the absurd. A breath of misalignment, billionths of a meter, would smear the scene and bury the planet again. Engineers talk about contrast, like mountaineers talk about altitude. For worlds tucked close to their stars, the planet can be 10 billion times dimmer than the light beside it. Imagine spotting a lone candle next to a stadium array during a night game, and you're still being generous. Yet with coronagraphy, that impossible becomes routine enough science. Not easy, but repeatable, testable, shareable. Blocking the blaze is only the first act. Even a perfect mirror carries microscopic ripples. Every ripple throws speckles, false glints that masquerade as planets. To sort truth from artifact, the system leans on wavefront control. Deformable mirrors flex ever so slightly, sculpting the incoming wave until the speckle field collapses. Algorithms, trained to recognize the specific fingerprints of optical ghosts, whittle away the rest. It's part optics, part statistics, part patience. All of it rides on the telescope, holding still with near impossible grace, pointing so steadily that if you aimed a laser from Webb toward the moon, you could keep it on a dime. Drift and the whisper blurs. Vibrate and the whisper is gone. Coronagraphy opens a window not only to bright, far-flung giants, but to the class of worlds that feel closest to home. For K2-18b, Webb mostly listens through transits, reading starlight filtered by air, rather than photographing a tiny crescent. Yet, the same philosophy applies. Tame the star, elevate the planet. Today's instruments can reveal broad strokes: water, methane, carbon dioxide, perhaps even the faintest hints of biogenic chemistry. Tomorrow's will go further. New coronagraphs and their bolder cousins, star shades, flying as separate spacecraft, promise to peel back enough glare to hunt Earth-sized planets around sun-like stars to pull spectra from worlds that, until now, were only the stuff of longing. While the light-shaping story unfolds, K2-18b itself tells a second, weightier tale, one about mass, gravity, and the quiet advantages of being big. This planet carries roughly 8.6 Earth masses, hefty by our standards, more akin to a scaled-down Neptune than a supercharged Earth. Instinct says, too large, too crushing, but physics answers more gently. Strong gravity is a keeper of things. It clutches atmosphere with both hands, thwarts the erosive tantrums of stellar winds, and holds on to water that smaller worlds slowly bleed to space. Where Mars lost air, a world like K2-18b hoards it. Where Earth will one day leak its reservoir into the void, this world can refill losses from the deep, hydrogen-rich ocean that shares a border with the sky. That gravity reshapes the interior, too. Instead of an iron heart like ours, pressures may have kneaded the planet into stratified layers, a high-pressure ice mantle deep below, overlain by a global ocean hundreds of miles thick, capped with a broad, insulating atmosphere. Picture an ocean that never ends, not as a surface feature, but as a planetary identity. In such volume, evolution isn't confined to coastlines or fragile shallows. It is free to sprawl, to layer, to invent robust cycles that repeat across a world's circumference. Mass buys time in another currency: heat. Larger planets cool slowly. Their interiors keep murmuring long after smaller brethren fall quiet. That lingering warmth can drive circulation, outgassing, mineral cycles, geologic processes that refresh a sky and feed a sea. Earth's inner fire will one day wane. Plates will stall. The carbon cycle will falter. A super-Earth can remain lively for spans that outlast civilizations, continents, perhaps even species as a concept. When a planet keeps renewing its air and stirring its waters, habitability stops being a narrow window and becomes a wide terrace. There's a sweet boundary in these sizes. Too small, and a world goes barren. Too large, and it swells into a mini Neptune with crushing depths of gas. K2-18b sits in the liminal zone, big enough to carry a thick protective atmosphere, and deep ocean, not so big that the bottom vanishes into metallic hydrogen. From orbit to core, the physics keep saying the same thing: stable, buffered, generous. Gravity's embrace also tempers the tantrums of a star. Even if a rare flare breaks from K2-18's calm surface, the planet's dense envelope absorbs, scatters, and converts that burst into heat before it can slash the sea with sterilizing light. The night side, locked in darkness by tidal coupling, doesn't freeze into an airless tomb. Winds ferry warmth around the globe until the idea of a harsh side loses meaning. Day beams crimson, night glows in hushed infrared, and the terminator, the ring of eternal dusk, becomes a long, habitable shoreline between light and shadow. In air this thick, chemistry becomes architecture. Methane doesn't merely leak from vents or microbes. It joins hydrogen and carbon dioxide in a durable, planet-scale conversation. Some of it may rise from biology, some from geology, all of it folded into climate. High overhead, conditions can squeeze carbon into tiny crystals that drift downward diamond rain, the sort of weather that would read like poetry in a school book here. None of it is magic. It's pressure, temperature, and time working together without hurry. From a distance of 120 light years, we read these truths the way one reads a letter carried too long in a pocket creased, faded at the edges, but legible with care. Coronagraphs subtract the glare, transit spectra, measure the breath, deformable mirrors, calm the speckle storm, algorithms sift, skeptics test, and a portrait coalesces, not a twin of Earth, but a cousin with enviable traits: thick skin, deep seas, steady sun, endless time. The philosophy running through all of this is as important as the machinery. Learning to hide a star so a planet can be seen is more than an optical trick. It's a way of thinking. Remove what overwhelms, and the subtle will reveal itself. That logic builds instruments, but it also builds humility. For a long while, we assumed habitability meant like us, a narrow invitation list written by a single world. K218b answers with a wider guestbook: hydrogen oceans that don't boil away, atmospheres that refill themselves, gravity that keeps its promises, chemistry that writes unfamiliar but fluent sentences. The more we look, the more the galaxy feels like a garden that prefers perennial beds to annuals, slow blooming, resilient, patient. With coronagraphs growing sharper and mirrors growing wider, we're about to count far more of those beds. Some will be too cold, some too hot, some wrapped too tight in gas. But some, many, if statistics hold, will play the same balanced chord we hear here. Long-lived stars, big but not too big planets, seas that keep their shape, skies that hold their ground. And in the quiet behind all the engineering, a simple image, a candle beside a stadium light, seen from the far side of a continent. The candle's flame doesn't change. Our willingness to shape the light around it does. We bend the glare, we flatten the speckles, we steady the hand. At last the candle comes into view, not bright, not boastful, simply present. A world where gravity is a shelter, not a weight, where water and air trade places without loss, where life, if it has begun, has everything it needs to take its time. Call it a revolution if you like, but it feels more like clarity. We're not chasing Earth's mirror image anymore. We're meeting Earth's sturdier cousin, larger, calmer, longer-lived circling, a star that will still be shining when our oceans are memories. And because we've learned to coax a searchlight into silence, we can finally hear the firefly. Sometimes the universe reveals itself not through what it shows, but through what it withholds. The latest clue didn't come as a bright signal or a clean spectral line. It came as an absence, a quiet ring in the dust around a young star called CE Antliae. Where light should have scattered evenly, Webb saw a gap, a clean, improbable circle carved through the star's debris disk. That hollow wasn't emptiness, it was a signature. Something unseen was shaping the chaos, sweeping a path through cosmic dust like a child dragging a stick through sand. Debris disks are the leftover scaffolding of creation. the raw material planets grow from. They're made of ice, rock, and powdered stone, orbiting their star in vast rings that glitter faintly in infrared light. Most stars wear them briefly, shedding their dusty veils as planets coalesce and clear the mess. But when Webb turned its mirrors toward CE Antliae, a young, restless sun, still surrounded by its natal cloud, it found 3 elegant rings, perfectly spaced, separated by clean, dark bands. That symmetry was suspiciously unnatural. Nature loves patterns, but it rarely makes them this neat without help. The view was especially revealing because the system lies almost face-on to us. We see the entire structure laid flat, like a painting, instead of an edge-on slice. In one of those dark gaps, Webb's infrared vision caught a faint ember of light, a small warmth that didn't belong to dust or gas. It was, unmistakably, a planet, a young one, Saturn-sized, sitting precisely where simulations had said a planet must be to carve that gap. The newborn world is still shaping its home, sweeping debris into sculpted rings and drawing lines across the disk like a cosmic gardener tending freshly planted soil. The discovery is quiet, almost tender in its simplicity. We can now find planets not only by their light or by the wobble they induce in their stars, but by the absences they create, the holes they clean in the dust around them. A planet's shadow can be louder than its shine. This new method, direct imaging through the architecture of debris, turns telescopes into archaeologists. Instead of waiting for the rare alignment of a planet crossing its star, astronomers can now read the blueprints of young systems directly, identifying worlds still under construction. Webb, with its exquisite infrared sensitivity, can peer through the veil of dust to watch worlds mid-formation, cradles of stone and gas, warm and wild. We're no longer just finding planets, we're catching them in the act of becoming. The planet in CE Antliae's gap seems young, hot, and heavy, a world still glowing faintly from its own birth. Its temperature, around 120 degrees Fahrenheit, sits within that narrow band where liquid water could someday exist. If the numbers hold, it lives inside its star's habitable zone, a region neither scorched nor frozen, balanced just right for chemistry to get ambitious. In time, its clouds might cool, its surface stabilize, its atmosphere settle into a rhythm that could cradle life. We may be seeing the prelude to a story that takes billions of years to unfold. For the first time, Webb allows us to witness this slow cosmic choreography. Stars still building their families, planets gathering dust like memories. It's humbling. We used to think planetary formation was ancient history, a process completed long before humans appeared. Now we can watch it happening, quietly and continuously, all across the galaxy. Creation isn't a chapter long closed. It's a present tense. The discovery around CE Antliae wasn't an isolated marvel. It was part of a widening pattern. As Webb continued its survey of nearby stars, something astonishing emerged. Worlds that could support life are not rare, not even special. They are everywhere. Within 200 light-years, our local neighborhood in galactic terms, astronomers have found more than 50 planets that show signs of habitability. Some are rocky, like Earth. Others are vast, super-Earths, wrapped in thick air. Each one holds a different chemistry, a different balance of light and warmth, a different answer to the same question. What does it take for matter to awaken? The diversity is dizzying. Some of these worlds circle close to their stars, hot and humid. with dense atmospheres that trap heat and keep water liquid even at boiling temperatures. Others drift farther out, where sunlight is faint, but internal heat or thick blankets of gas keep their seas from freezing. A few gleam white with ice, hiding dark oceans below their frozen crusts. Subsurface worlds that never see the sky, yet may harbor ecosystems richer than our own. It's not just the number that stuns, but the variety. Each star shapes its zone of life differently. Around red dwarfs, the habitable zone hugs close and endures for trillions of years, giving life near infinite time to experiment. Around larger, brighter suns, the window is brief but intense, a crucible where evolution might race instead of drift. Every system becomes a different experiment in possibility, a cosmic gallery of evolutionary paths we can only guess at. If 50 potentially life-friendly planets exist within our small sphere of space, then scale that to the Milky Way's 400 billion stars, and the numbers swell into poetry. The galaxy could hold billions of living worlds, perhaps more living worlds than there are living beings on ours. It's a staggering idea that life might be as common as starlight, not a rare spark but a habit of the cosmos itself. Each world would tell its own story. Some may breathe oxygen and exhale carbon dioxide like Earth's forests do. Others might rely on methane or hydrogen, their metabolisms running on chemistries alien to us, yet perfectly sensible there. Some might know gravity 3 times ours, their creatures built low and strong. Others might exist under skies so dense that flight is trivial. There may be planets of constant twilight where photosynthesis hums under red suns, or dark worlds where life glows softly in eternal night. And then there's the larger question. If life is this common, how many of those living worlds learn to look back? If biology repeats itself often enough to fill the galaxy, intelligence might not be rare at all. It might be another step in a long, patient sequence the universe likes to take. Somewhere, perhaps on K218b or CE Antlia's growing planet, or in the icy oceans of a world we haven't yet named, there could be minds asking the same question, wondering if the faint blue dot they've detected around a yellow star might also harbor thought. Our oldest radio signals, those first uncertain broadcasts from a century ago, are just now reaching some of these nearby systems. Maybe, even now, those signals are washing across a red dwarf's planets, carrying the crackle of our beginnings. If anyone is listening there, they're hearing echoes of a species just learning how to speak to the stars. And as we listen back, reading light and shadow with Webb's patient eyes, it feels less like searching for others and more like recognizing kin. The picture that's forming is immense and intimate at once. Planets carving rings in dust, young stars building their families, oceans settling under red light, worlds breathing, thinking, waiting. Life, it turns out, may not be the exception, it may be the universe's favorite trick. Given the right mix of warmth, chemistry, and time, existence seems to insist on itself. We once looked up and saw emptiness. Now we know that the darkness is crowded with planets, with atmospheres, with possibility. Each speck of light could be a sun with its own retinue of living worlds, each one unique, each one quietly proving that creation is not finished. The cosmos is not silent. It's humming a soft, unending chorus of becoming. Water carries memory. It remembers heat and cold, remembers the pull of gravity and the hush of pressure. On K218b, That memory fills a world. The first clues were in the air, light from a distant star passing through an atmosphere and returning to us softened, with tiny colors missing, where H2O had sipped them away. Those gaps in the spectrum said a simple word we know by heart: water. But the amount implied something far larger than lakes or seas. It hinted at an ocean that does not end hundreds of miles deep, a planet wrapped in liquid from pole to pole, a blue so heavy it would sink our bravest ships before they could say hello. The water there is not the water you pour from a glass. Hydrogen from the sky dissolves into it, thickening the recipe and widening the range where liquid can remain itself. On Earth, water keeps its balance over a narrow span: freeze at 32, boil at 2 to 112 Fahrenheit. Add pressure and impurities, and the window stretches a little. On K218b, it stretches a lot. The hydrogen-enriched ocean holds together from near freezing to well above the boiling point we know, a patient solvent that refuses to choose between ice and vapor. In that long middle, chemistry has room to explore. Molecules find one another more often. Reactions run with steady eagerness. And life, if it has taken root, has more than comfort. It has freedom. Depth is not an enemy there. On Earth, pressure makes the deep a place of steel-bending force, where only specialized creatures can survive. In K218b's sea, dissolved hydrogen acts like a cushion, changing how water compresses, keeping it friendly to motion and exchange even far below. Picture layers upon layers, a sunlit skin the color of rusted dawn, a broad twilight where light is an idea more than a fact, and then the slow warm dark where heat moves like thought. Each layer is a different promise. Each one could host communities that never meet, yet rely on the same quiet cycles of carbon and sulfur and nitrogen slipping between water and air. This ocean does not simply sit, it participates. As hydrogen leaks away to space, the sea gives more, replenishing the sky and keeping the planet's blanket thick. Earth is losing water, grain by grain. Sunlight splits it, and hydrogen escapes forever. Given enough ages, our oceans will shrink. K218b's gravity and chemistry conspire against that fate. The atmosphere is a reservoir connected to the sea, and together they hold on. Longevity, the rarest gift, becomes ordinary, their oceans and air retained, not for millions, but for spans that outlast stars. Temperature helps. Around 120 degrees Fahrenheit reads hot to our skin, but kind to molecules. Speedy enough to push reactions along, gentle enough that the delicate folds of complex organics stay folded. Imagine a planet-sized hot spring tuned to keep going. In such warmth, cells, if there are cells, wouldn't need to sprint through the day to stay alive. They could invest in intricacy, longer chains, nested cycles, systems that talk to one another across distance, with pulses of chemistry and heat. The water carries carbon, too. Oceans breathe it in, hold it, and send it back in moderated breaths. On a world this wet, that exchange becomes a thermostat. When the air grows rich in CO, 2 more dissolves. When it thins, the ocean returns what it kept. Add the slow work of geology, minerals reacting with carbonic acid, travelers carrying carbon down to heat and back up again, and the climate gains a kind of memory. Not the sharp memory of weather, but the slow memory of climate that helps a world keep its balance across ages. Complex life loves that kind of steadiness. It grows bolder when the floor beneath it doesn't tilt without warning. If super-Earths like this are common and the sky keeps telling us they are, then the universe may be a library of oceans, not a handful of blue dots, but whole shelves of them, each with its own recipe, its own patience, its own version of alive. We have been looking for puddles. The cosmos appears to prefer seas. Starlight carries the proof gently. When a planet crosses its star, a sliver of light filters through the air above its sea and gathers the planet's fingerprint. Astronomers call it a transmission spectrum, but what it really is feels intimate. The breath of a world recorded in color. Water leaves one set of shadows, methane another, carbon dioxide a third. Arrange those shadows along wavelength, and a pattern appears, bars and valleys, like a song on a staff. Webb's instruments, cooled until noise becomes a whisper, measure the depth of each note to parts per million, as if trying to hear a single flute in an orchestra the size of a stadium. What makes this music remarkable isn't just the presence of certain notes, it's their coexistence. In a dead atmosphere, left alone for long enough, chemistry drifts toward calm. Reactive partners meet and neutralize each other. Free energy is spent. The mix settles. Earth refuses that calm. And so, if we're reading right, does K218b. Gases that should eat each other persist side by side. That disequilibrium is not a proof, but it is a hint with a shape we know. Here, oxygen and methane coexist because photosynthesis and metabolism keep refilling both buckets. There, hydrogen and methane and other organics may be maintained by loops. We have not yet mapped loops that only life runs with such regularity. Among the lines Webb reported, one set drew more breath than others, a pattern consistent with dimethyl sulfide, a molecule that, on Earth, is spelled out by living things. Our seas make it, our skies catch it, clouds bud from it, climate listens to it. It also breaks down quickly. For it to linger in any atmosphere, something must be making more now. That was the soft thunder in the data. If a similar molecule truly floats in K218b's air, it cannot be a fossil. It must be a present tense verb. Caution lives beside wonder, as it should. Unknown chemistries, unfamiliar catalysts, lightning and minerals and heat, each could write tricks we haven't learned to spot. The models improve, the measurements repeat, signals strengthen or fade. But whether dimethyl sulfide stays in the final draft or gives way to a cousin, the broader story does not dim. The atmosphere looks busy in a way that resembles life at work, not matter asleep. The spectrum reveals more than ingredients. It implies kitchens. High hydrogen and methane suggest metabolisms that do not need oxygen's violence to gain energy. Organisms, if they exist, might breathe the ocean itself, harvesting dissolved hydrogen, exhaling compounds that in turn tweak clouds and temperature. Photosynthesis might favor longer wavelengths, pigments tuned to a redder sun. Life could be dark-skinned in every sense, absorbing as much as it can from a dim sky, trading brightness for efficiency. None of this is certainty. All of it is a working map that fits the landmarks we've drawn from light. To read such subtleties demands steadiness, bordering on devotion. The telescope must keep its gaze still to a fraction of an arcsecond. Detectors must count leagues of photons without losing track of a single one. Data pipelines must untangle the star's heartbeat and the instrument's sigh from the planet's breath. It is like picking a particular raindrop from a river and naming where it began. Yet, the discipline pays off. What was once blank becomes textured. What was rumor becomes curve and number and, eventually, meaning. First chemical signature of extraterrestrial life is a phrase that belongs to history books more than lullabies, and it must be earned with proof layered as carefully as Webb's mirrors. But something softer and no less important is already true. We have learned to listen for life with light, not for cities or signals, not for machines or messages, but for atmospheres refusing to rest. For worlds that keep themselves off balance on purpose because living things like the air that way. Return, then, to the ocean. Picture a droplet leaving the surface, rising into a sky thick with hydrogen, meeting sunlight, breaking apart, joining again. Picture a molecule of carbon dioxide dissolving and later returning, temperature riding up and down with its tide. Picture dim hints of sulfur compounds moving from sea to air and back, seeding clouds that cool the water that made them. 1,000 cycles nested together, each one small, together enormous. Oceans this vast do not merely cradle life, they collaborate with it, letting a planet tune its own weather like an instrument. K218b may never know continents or beaches. Its shores could be boundaries of pressure and chemistry instead of sand. Yet it has what matters: a solvent that remembers, an atmosphere that participates, heat that stays inside the gentle. It has time more than enough for complexity to try, fail, and try again until the trying becomes a tradition, and it has a sky that tells on it. When starlight passes through that sky, it returns to us carrying the handwriting of a world in motion. The night is very old, and it is very patient. In that patience, water on a super Earth can become more than a setting. It can become an author. If the spectrum we're reading belongs to a living planet, then life, there is not a decoration. It is an engine, tuning the air, glinting in the light, leaving a trace strong enough to cross 120 years of darkness and still be legible when it lands. That is the quiet miracle Webb lets us share. Not a shout from the void, but a steady imbalance, a persistent fragrance, the chemistry of breath captured in gold and shadow, and understood as the simplest story of all. Something is making more of itself, again and again, under a red sun, in an ocean that refuses to end. The star called Ce Antliae is very young, only a few million years old, and it wears its youth like a bright fever. Around it, a broad disk of dust and ice circles quietly, and within that disk, the shapes of future worlds are beginning to appear. The scene looks peaceful in infrared light, but it is anything but calm. Grains collide, fuse, fracture, and try again. Fragments melt in brief flashes of heat, and then cool into new forms. It is a nursery with the lights dimmed, noisy, complicated, full of promise. Young red dwarfs are spirited creatures. They flare without warning, releasing bursts of energy that can bathe nearby space in radiation for hours or days. To a forming planet, those storms are both threat and gift. Too much can strip an atmosphere. Just enough can crack molecules into lively fragments, radicals eager to reassemble into more complex shapes. On Ce Antliae's newly found world, where the air hovers near 120 degrees Fahrenheit, those flares may have acted like a match, struck over and over above a bowl of ingredients, helping chemistry climb the ladder from simple to intricate. It is a harsh kindness, the kind that creation often offers. The disk itself tells a story in rings, seen almost face on, It's as if we're looking at ripples on a pond from above, three bright bands of material separated by clean, dark lanes. In the innermost ring, the dust is fine, a smoke of stone and ice. Farther out, the particles have grown into pebbles and fist-sized clumps, then into bodies big enough to pull on one another with more than a whisper. Out beyond that, the third ring gleams with pristine stock grains not yet collected, ice not yet melted, raw material waiting its turn. Between the first and second rings lies a gap so tidy it seems deliberate. That emptiness is the planet's signature, a track carved by gravity, the way a skater's blade carves a clean line on black ice. The planet sits in that lane like a shepherd, sweeping its orbit clear as it circles, and in the same motion pushing leftover debris into the bright rims that frame the void. Where orbits resonate, places where particles round the star, in simple rhythms compared to the planet's year material, can gather and survive. Computer models sketch out those safe harbors in elegant spirals and arcs. Webb's image, when laid atop those predictions, hums with agreement. The rings sparkle exactly where the equations said they would. The world is not drifting through its disk by accident. It is sculpting, arranging, encouraging order in the dust around it. Order does not mean gentleness. In the middle ring, collisions are common. Pebbles strike and stick, or strike and shatter, or strike, fuse, and then crack along a new seam, warmed by the energy of impact. Each crash is a tiny furnace, briefly driving temperatures high enough to reshape minerals, release trapped volatiles, and make fresh surfaces that react more easily. When fragments rain down on the growing planet, they bring both heat and inventory. Water ice from comets, carbon-rich grains from the cold outer regions, metals from the inner ring's rocky stock. The world gathers these gifts into layers, some sinking, some floating, some dissolving into atmosphere or ocean. Every delivery is a chance for chemistry to take a longer stride. The star's light, though temperamental, helps in other ways. Ultraviolet photons break apart simple molecules in the air, and the pieces, free hydrogen, excited carbon, eager oxygen, quickly seek partners. In that fast reshuffling, larger organics can form. Methane might fracture into chains. Carbon dioxide might help build aerosols that seed clouds. Sulfur compounds from icy bodies might join with carbon to create molecules that nudge climate and cloudiness. None of this requires life, not at first, but it writes a stage that life could later inhabit, with gradients of energy and chemistry that living systems love to exploit. The gap's precision is worth lingering on. Theory long predicted that a forming planet would clear a trench in its birth disk. Yet, the sweep around CE Antliae is unusually clean, as if the world has been at its post longer than we expected for such a young system. Clean edges mean repeated passages in the same path. They mean a stable orbit. They mean time on the scale of millions of years for gravity to practice its choreography and refine it. That tidiness also hints at a mass, heavy enough to hurt stones and ice, light enough not to stir everything into chaos. The estimates land near Saturn-like heft, a sweet spot for clearing and shaping without blowing the disk apart. The materials the planet has captured whisper about its future: water-rich comets, carbon-laden pebbles, salts and organics that survive the dive inward. All of them add volatility to the world's recipe. Volatiles make atmospheres. Atmospheres make weather. Weather transports heat and chemistry across the globe. At temperatures around 120 degrees Fahrenheit, water would not be scarce. It would rise and fall, evaporate and condense, trade energy with the air in grand loops that keep the planet's face from splitting into extremes. And because the system is young, the supply line from the outer ring remains open. More water, more carbon, more sulfur, more chances. Even violence has a rhythm when gravity conducts. The planet clears its lane. The rings brighten. The star flares. The atmosphere sizzles with new fragments. Clouds thicken and thin. Impacts deliver energy. The crust flexes. Gases vent. A fresh layer of haze forms and drifts. Over time, this cycle can build a stable imbalance. A planet that refuses chemical rest. An air that stays just out of equilibrium for long spans because sources keep refilling the shelves that reactions would otherwise empty. It's in that restless balance that life often steps in, taking over the job of refilling, tuning, and maintaining. We don't yet know the day-to-day weather in those rings or on the hidden world, but the architecture already tells us the big pattern. The presence of a planet sets the disk into order, and that order feeds the planet in return. The world is not a passenger, it is a choreographer. The lanes it vacuums turn into highways where other bodies can travel safely. The resonances it sets up become cradles where future moons or companion planets might gather. The system we see, with its nested rings and clean spaces, is not chaos slowly settling. It is design, emerging a gravitational blueprint, inked by countless orbits. There is comfort in that order, even amid the youth and fire of the star. It means that planet building isn't only a series of accidents, it is a process with preferences. Rings prefer clarity at certain radii. Particles prefer to keep time in certain ratios. Gaps prefer to be clean. Out of those preferences, longevity grows. A world that establishes tidy boundaries early can keep gathering material without being battered to pieces. A disk parceled into lanes is less likely to collapse inward or disperse too quickly. Time expands, and with it, the chance for complex chemistry to keep compounding. From our distance, we see only the broad strokes, a young red star, a bright, face-on disk, a neat gap, a faint ember in the lane. Yet within those strokes lies an intimate suggestion. Worlds may be able to begin their long habitability far sooner than we thought. We once imagined that life needed quiet, a star past its tantrums, a system fully settled. Andlier hints at a different recipe, purposeful mess, guided by gravity, energized by flares, cooled by rings. In such a place, biology and geology would grow up together, rock and atmosphere co-evolving, chemistry and climate teaching each other tricks. Consider the planet's present warmth. At 120 degrees, water can move quickly through cycles without tearing itself apart. Organics can form, test, and survive. Membranes, if any exist or will exist, could remain flexible and functional. If an ocean forms, it will speak often with the sky. If clouds thicken, they'll return shade to the surface that made them. Each loop ties into the others until the world becomes a network of exchanges rather than a collection of parts. That is how resilience begins, in many small trades that add up to steadiness. The gap story reaches still further. Its sharp borders and resonant rims are not only signs of a single planet, they're hints that the surrounding rings might be incubating others. Where one world carves, another might be condensing. The architecture suggests neighborhood, not solitude, a system with lanes for traffic and room for families. If that bears out, CE Antliae could host a suite of planets across a range of distances and temperatures, each with its own experiment in habitability, each borrowing light from the same long-lived star. For now, the most striking fact is that absence millions of miles of well-kept emptiness told us where to look. We found the world by finding its footprint. We read its mass in the width of a void, its age in the cleanliness of a border, its influence in the way dust obeys unseen hands. It is a gentle reminder that discovery can come from quiet clues. When we learn to notice where matter is not, we unlock where it must be. In the coming years, more images will sharpen the scene. We'll map the disk's grains by size, trace the chemistry of the gas between them, time the star's flares, and watch the atmosphere respond. We'll nudge models and see which harmonies hold. Perhaps the planet's temperature will drift a little warmer or cooler. Perhaps its mass estimate will settle. Perhaps another faint ember will appear in the next gap out. Whatever arrives, the melody will remain. A young system already showing the grace of structure. A newborn world acting as an architect, and the old pattern of creation repeating itself in a new key. In the soft dark where we imagine this system, it's easy to picture the scene as a slow dance. Dust swirls, rings glint, the star flares and rests, the planet circles and clears. What looks hostile at first, radiation, impacts, chaos, becomes a set of tools. Flares write chemistry, collisions deliver ingredients. Gravity draws clean lines for stability. Temperature holds steady enough for bonds to form, break, and form again. The crucible is not an obstacle. It is the first teacher, insisting that any life that comes later will know how to bend without breaking, how to use violence as fuel, how to thrive where newborn stars breathe hot and fast. So the gap stays empty, and because it is empty, it speaks. It tells us a planet is there, that it has been there long enough to tidy, strong enough to shepherd, patient enough to build. It tells us that planetary systems can be both fierce and careful at the same time, and it hints that the road from dust to dwelling may be shorter and more common than we dared to hope, written not only in what shines, but also in what the light has learned to leave out. Across the growing catalog of habitable worlds, one number keeps returning like a refrain: 120 degrees Fahrenheit. It shows up in the atmospheres of super-Earths, in the shallow seas of hydrogen-shrouded worlds, in the equations that describe warmth balanced against light. The universe seems to favor it, as though it has found a single comfortable key in which to write the song of life. Warm enough for chemistry to move quickly, cool enough for complexity to stay intact, heat that invites motion but does not destroy it. Water behaves differently at that temperature. Its bonds loosen just enough to dissolve more kinds of matter, turning it into an exquisite solvent for biology's chatter. Nutrients, waste, and signal molecules can all travel faster. Reactions hum along at a tempo that feels alive, but not frantic. The liquid's viscosity thins. Diffusion sharpens. Membranes, if there are membranes, become supple without tearing. It is a range where metabolism becomes music, fast enough for growth, slow enough for stability. And there's a deeper echo here. On Earth, 120 is the warmth of creation's hidden workshops. At the bottoms of oceans, near hydrothermal vents, water glows with that same heat as it seeps through volcanic rock. There, life on our planet found its oldest foothold. Bacteria harvest chemical energy instead of sunlight, weaving ecosystems in perpetual night. They thrive at the border where water, heat, and minerals meet a temperature that coaxes molecules into cooperation without scorching them apart. If worlds light years away rest in that same gentle fever, they may be echoing the conditions that birthed us. In laboratories, scientists have seen the same magic. Amino acids, the first letters of life's alphabet, assemble most easily at these warm midpoints. Too cold and reactions crawl to stillness. Too hot and the fragile chains unspool. Around 120, molecules try, fail, and try again, often enough to invent something new. It's as if chemistry, when given that degree of freedom, begins to dream. Different planets arrive at this perfect balance in different ways. Some trap heat beneath blankets of hydrogen or carbon dioxide, their atmospheres holding light the way wool holds warmth. Others glow from within, radioactive decay, tidal flexing, or the slow compression of gravity, keeping their cores alive long after starlight fades. A few use both heat from above and below entwined into a long equilibrium. However they get there, the pattern repeats. A steady warmth where liquid water, quick chemistry, and patient time coexist. It may be coincidence. It may also be a rule, so universal, we are only now learning its name. If temperature is the metronome of life, 120 keeps perfect time. The pace accelerates evolution just enough. Mutations arise a bit faster. Metabolisms turn over more energy, and ecosystems can recover swiftly from change. The environment remains stable enough not to erase its own experiments. A planet at this temperature does not merely allow life, it encourages it, pushing it toward diversity. On such worlds, evolution could dance more freely than it ever has on Earth, filling oceans and skies with possibilities we can scarcely picture. Some see this pattern and whisper about tuning a universe adjusted for life, not by miracle, but by inevitability. Just as stars settle into sizes that let them burn with long grace, perhaps planets settle into climates that invite biology to take the stage. The repetition of that number across star systems might not be coincidence at all, but resonance, physics and chemistry meeting in the same quiet agreement again and again. And yet, warmth alone is not the story. It's what fills that warmth that astonishes us. Take K218b. In its atmosphere, Webb found something that shouldn't be there: methane. On Earth, methane lives briefly. Sunlight tears it apart. Ultraviolet light scatters it into simpler fragments. It lingers only because living things keep remaking it: swamps bubbling it up from the slow decay of plants, microbes exhaling it deep in the mud, animals releasing it as their own byproduct. Geology contributes a whisper, but biology shouts. Without constant renewal, methane disappears. So when Webb caught thick traces of it high in K218b's sky, something didn't add up. The planet sits close to its red dwarf sun, bathed in enough radiation to shred methane within years. Yet there it was, plentiful and persistent, woven through hydrogen clouds that should have diluted it away. The simplest answer, the only one that fits the data cleanly, is replenishment. Continuous, large-scale production. A world exhaling life's simplest signature. If that's true, the scale is staggering. The measured concentrations suggest a biosphere busy enough to reshape its atmosphere entirely, far outpacing Earth's output. On our planet, methane makes up a tiny fraction of air. On K218b, it seems abundant, mixed with water vapor and dimethyl sulfide in ratios that can't be purely mechanical. The planet's biology, whatever its form, is not surviving on the margins. It is thriving, altering chemistry on a planetary level. Methane there may play the role oxygen does here, a working gas for respiration, a carrier of energy through ecosystems that never see a sunbeam. In that hydrogen-rich air, it could be both food and breath, oxidizer and fuel. The whole atmosphere might be alive, a gradient of metabolism stacked like ocean layers, each one feeding the next. Organisms at lower levels could harvest methane. Others, higher up, might release it. Still, others might use the heat from reactions between methane and other gases to power strange cycles of growth. Life might be vertical, not horizontal, an atmosphere turned into an ecosystem. Even if methane is not biological, its presence still paints a portrait of complex chemistry. In laboratory flasks, when hydrogen and methane mingle under the kiss of ultraviolet light, amino acids form spontaneously. Add pressure, a touch of water, and time, and the results grow richer: rings of carbon, chains of nitrogen, sugars. On K218b, that laboratory spans an entire planet. The sky itself could be an ongoing experiment, forever generating the compounds that living things require. The persistence of methane also speaks of stability. To sustain it for millions of years, a planet's climate must hold steady. Its atmosphere must renew rather than collapse. Its chemistry must repeat without exhausting itself. That long-term steadiness allows evolution the quiet patience to turn chemistry into ancestry. Life there, if it exists, has likely been refining itself for epochs. The mystery deepens with the discovery that K218b's air contains not one or two simple gases, but a tapestry of them interacting like voices in harmony. Hydrogen, methane, carbon dioxide, and traces of dimethyl sulfide form a complex circuit of reactions that may support several kinds of metabolism simultaneously. One species might exhale what another breathes. One's waste becomes another's nourishment. The atmosphere ceases to be a backdrop. It becomes the organism, the collective breath of a planet. To look at that spectrum of gases is to see the pulse of an entire biosphere written in light. That thought changes the way we picture habitability. Life does not have to cling to rock or swim in oceans. It can fill the sky, ride convection currents, and drift through chemical gradients that supply all the energy it needs. A thick atmosphere, once considered a barrier to observation, might in fact be the most generous home for life, protecting it from radiation, recycling elements endlessly, and making itself visible from light years away through its restless imbalance. In this way, K218b's methane is not just a clue, it is an invitation. It reminds us that planets breathe, that chemistry can learn rhythm, that the line between environment and organism may be thinner than we think. The planet's air does not sit still. It loops, reacts, corrects, and maintains a dynamic system indistinguishable from metabolism on the largest possible scale. To glimpse that through a telescope is to feel both awe and kinship. The same warmth that fosters our oceans hums there. The same molecules that build our bodies circulate in its clouds. The same fragile disequilibrium that defines life keeps its air unbalanced. We are witnessing, perhaps for the first time, a mirror of our own planet's breath, written in alien syntax. 120 degrees Fahrenheit, the temperature of hydrothermal vents, of stable enzymes, of planetary comfort, seems to echo through it all. It is the warmth of creation repeating itself from world to world, a cosmic refrain. At that temperature, methane lives, water moves, carbon binds, and evolution, wherever it arises, finds its stride. The universe, it seems, does not merely allow life, it encourages it with perfect consistency, setting the thermostat again and again to the same gentle heat and waiting patiently for the next world to stir and begin to breathe. The discoveries made by the James Webb Space Telescope are not the end of a story. They are the opening of a door. What we've seen on K218b and on a handful of other promising worlds is only the first whisper of a grander conversation between stars and life. Having proven that living chemistry can be sensed across interstellar distances, astronomers are now preparing to listen in earnest. The next decade will be a symphony of observation, analysis, and wonder. This new effort, known simply as the Biosignature Survey, will be the most ambitious campaign in the history of astronomy. Its goal is not to find one habitable world, but to map the abundance of life across the local galaxy. Webb, along with its successors and companions, will target more than 200 nearby star systems, every one within 100 light-years of home. Each system will be examined for the faint chemical fingerprints that only living worlds seem to produce. Methane mixed with carbon dioxide, dimethyl sulfide beside water vapor, oxygen in the company of gases that should consume it. The presence of any one molecule may not prove life, but their combinations tell stories that only biology can write. Until now, astronomers relied mostly on luck. A planet needed to pass directly between us and its star so that its atmosphere could backlight itself in the starlight. The new campaign will stretch far beyond that constraint. Webb's upgraded observing modes will capture planets that never transit at all, reading the reflected and emitted infrared glow that spills into space from every direction. Sophisticated algorithms, trained on thousands of simulated planets, will comb the spectra, searching for complex blends of molecules that could hint at unfamiliar biochemistries, perhaps ones based on ammonia, methane, or sulfur instead of oxygen and carbon. The goal is not to recognize life as we know it, but to learn what alive can mean elsewhere. These studies won't stop at snapshots. They will unfold over years. By observing the same worlds again and again, scientists will track subtle changes in atmospheric chemistry, the seasonal breathing of alien biospheres. On Earth, vegetation alters our air each spring and autumn. Plankton blooms shift ocean gases. Microbes answer the turning of the year. If similar rhythms appear in the light of distant planets, they would reveal not just static life, but living cycles, ecosystems responding to their world's own seasons, their sun's moods, their ocean's tides. The universe would no longer look silent. It would appear to inhale and exhale. And yet, the search will reach even further into the realm of intelligence. Alongside biosignatures, astronomers are beginning to hunt technosignatures, the chemical fingerprints of industry itself. Certain gases, like nitrogen dioxide, chlorofluorocarbons, and other complex pollutants, have no natural origin. They linger as traces of machines, combustion, or synthesis. If any appear in the spectrum of a distant world, they would announce not only life, but civilization. It would be the quietest and most profound handshake in cosmic history, a meeting not of bodies, but of atmospheres. To make these discoveries credible, no telescope can work alone. Webb will coordinate with a fleet of partners. Giant ground-based observatories will watch in visible light for flickers that could reveal cities or artificial illumination on the night sides of worlds. Radio telescopes will listen for narrow-band transmissions from systems where Webb spots promising chemistry. Even small optical arrays will contribute, timing transits and measuring brightness variations. The campaign is becoming a multi-wavelength conversation space, and Earth working as one great sensor spread across the solar system. Meanwhile, engineers are already designing the next instruments to push the frontier outward. Future coronagraphs, refined descendants of the ones that helped Webb block starlight, will detect fainter, smaller, Earth-sized planets. New spectrographs will dissect light into finer slices, letting us read atmospheres in astonishing detail. And the data pipelines will grow ever more sophisticated, capable of teasing meaningful signals from what today still looks like noise. Bit by bit, we are building the first map of life in the galaxy, a chart not of stars alone, but of biospheres. Within a decade, we may know hundreds of worlds with chemical signatures that whisper, alive. Each will have its own balance of gases, its own evolutionary tempo, its own poetry of climate and chemistry. The universe will begin to look less like a cold void and more like a vast archipelago of breathing islands scattered through space. The question, are we alone, may finally lose its suspense. The answer will not be a single word, but a census. Far from these data streams, in the young system of CE Antlier, Webb has found another lesson about origins. Around that crimson star lies a sight both elegant and raw, a three-ring disk glowing in infrared, each band holding material at a different stage of becoming. It looks like a cosmic carnival, rings of dust, ice, and rock twined around their sun, each one tracing a chapter in the biography of worlds. The innermost ring hugs the star so closely that its grains glow white-hot. Temperatures soar high enough to melt lead, yet the particles remain, held in delicate balance between radiation and gravity. Here, fine dust grains collide and fuse into pebbles, and those pebbles cling together into clumps. These are the seeds of rocky planets, the first hints of solidity inside the glare. Farther out lies the middle ring, cooler, darker, rich with both ice and stone. This is the temperate workshop where variety thrives. Within it circles the newly discovered planet, its orbit carved clean like a lane in snow. The world's gravity has vacuumed much of the material nearby, but left behind enough debris to reveal what it's still building. Rock and ice continue to merge. The chemistry of potential oceans and atmospheres is already underway. In these mid-regions, silicates meet ices, carbon chains meet water, and the raw vocabulary of habitability takes shape. Beyond them all spins the outer ring, a deep frozen archive of the star's earliest material. Water ice, methane ice, and tar-dark organics remain untouched there, waiting their turn. Occasionally, gravitational nudges send some of this pristine cargo inward. Each impact delivers new volatiles, water, carbon, nitrogen, to the growing worlds inside. The outer ring is the cosmic pantry, keeping ingredients chilled until the inner kitchen is ready to use them. What looks like art is also mathematics. The spacing between the rings is not random. It follows the quiet logic of orbital resonance, each ring occupying a zone where the pull of gravity allows stable orbits, while the gaps mark forbidden regions where resonances would tear structures apart. The three-ring pattern sketches the architecture of a system obeying universal law. Matter responding to rhythm, chaos, self-organizing into order. Simulations of CE Antlia's disk show that this structure is alive with motion. Material from the cold outskirts drifts slowly inward, feeding the middle and inner zones. The newborn planet in the central ring acts as a governor on this flow, slowing it down, controlling its pace. Without such regulation, inner worlds might grow too fast and collapse. With it, growth becomes sustainable, measured, stable over millions of years. The planet's gravity turns what could have been a storm into a process. To watch such a system is to glimpse the making of order itself. Once, astronomers imagined planet formation as chaotic, collisions, accidents, debris flying every which way. CE Antliae suggests otherwise. The pattern repeats across the cosmos. Disks flatten, rings appear, planets carve gaps, material feeds inward. The process resembles not an explosion, but a symphony with recurring themes. Each note, dust, rock, ice, knows its cue. For humanity, seeing this structure is like catching a reflection of our own beginnings 4.5 billion years ago. The inner ring where rocky planets form could be the echo of what once circled our sun. The middle ring mirrors the zone that gave birth to Earth. The outer ring recalls our Kuiper belt, where frozen comets still carry the ingredients of life. What Webb shows us around CE Antliae is not alien, it is ancestral. The same cosmic routine playing again under a younger star. The campaign that will search for life and the observations of systems like CE Antliae belong to one continuum, from birth to breath, from dust to consciousness. The three-ring architecture is the prologue to the biosignatures we now detect elsewhere. The same forces that carve rings today carved our own history long ago, laying the foundations for oceans, air, and living chemistry. In that light, Webb's mission becomes more than science. It becomes autobiography. By watching other stars build their worlds, we are remembering how our own was made. By finding other atmospheres breathing, we are rediscovering what it means for a planet to be alive. The universe is not silent construction or sterile mechanics. It is a living manuscript, pages turning at cosmic scale, each ring and each spectrum another sentence in the same grand story. The world orbiting the young star CE Antliae is small by cosmic standards, yet its discovery has redrawn the map of what humanity can see. With a mass barely a third that of Jupiter, it has become the lightest planet ever, directly imaged around another star, a record that, not long ago, seemed out of reach. For decades, direct imaging was the privilege of giants, blistering super-Jupiters many times Jupiter's mass, blazing bright with the heat of their youth. They were the easy quarry in the glare of their suns. But this faint, subtle world has changed the game. Its dim light is 10 billion times weaker than its parent stars. To isolate it, the James Webb Space Telescope had to look past oceans of glare and confusion, teasing a soft ember from a storm of brightness. Detecting such a faint glow required Webb to operate at the edge of physics, every vibration damped, every mirror atomically aligned, every photon accounted for. What emerged from that darkness was not only an engineering triumph, but a scientific revelation. At 1/3 of Jupiter's mass, this world rests on the boundary between two planetary regimes. Heavier planets become gas giants, vast envelopes of hydrogen and helium, wrapped around deep metallic cores. Lighter ones tend toward solidity, rocky surfaces, thin atmospheres, the ingredients of habitability. This planet straddles the divide, offering a rare look at the transition between those classes. Understanding that threshold is vital because it tells us where life might find footing. A bit more mass, and a planet's surface hides forever beneath crushing gas. A bit less, and it loses its atmosphere entirely. Somewhere between lies balance. The new world seems to live in that balance. Its surface temperature, again the now familiar 120 degrees Fahrenheit, suggests a gentle greenhouse effect, strong enough to keep oceans liquid, weak enough to avoid runaway heat. It may have a solid core, perhaps a shallow atmosphere, maybe even a temperate sea. In that sense, it is less a miniature Jupiter than a distant cousin to Earth. Finding it was like listening for a whisper behind thunder. Webb's instruments had to separate the planet's faint infrared emission from the blinding scatter of dust in the surrounding debris disk. Algorithms trained on millions of simulations sifted the data, subtracting the star's light, then the disk's reflection, layer by layer, until the planet's tiny warmth remained. What we see now is not a bright sphere but a ghostly point, proof that the telescope's sensitivity can reach worlds we once believed invisible. Because its atmosphere is thin, scientists will be able to probe it deeply. Massive planets hide their lower layers beneath dense gases, but lighter worlds offer glimpses closer to the surface where clouds form, where chemistry thrives. Spectra taken over the coming years may reveal water vapor, carbon dioxide, methane, perhaps even the faint breath of biological activity. The discovery of such a low-mass planet proves that Webb is not limited to studying monsters. It can find and analyze worlds like those in our own solar system, perhaps even ones like us. This single observation has opened a door to a new era, a golden age of planetary exploration that will stretch across decades. Beyond Webb, entire generations of instruments are being prepared, each one sharpening the universe's focus a little more. The most ambitious among them is the Habitable Worlds Observatory, a future space telescope conceived expressly to find Earth-like planets around Sun-like stars. Where Webb sees with a contrast ratio of roughly 1,000,000 to 1, this new instrument will aim for 10 billion to 1, the difference between seeing a candle beside a searchlight and seeing a firefly beside that candle. With that power, it will be able to directly image true Earth analogs and study the light that filters through their skies. Within that light may be the unmistakable signs of water vapor, oxygen, ozone, and perhaps molecules no one has yet imagined. On the ground, another colossus rises, the extremely large telescope in Chile. Its mirror, over 100 feet across, will dwarf every previous optical instrument. This behemoth will dissect the spectra of nearby exoplanets with surgical precision, detecting dozens of molecular species and distinguishing, for the first time, the delicate fingerprints of biological activity from geological background. With telescopes like this, we will be able to map weather patterns on distant worlds, to see clouds move and storms form on planets orbiting other suns. To handle the flood of information such observatories will produce, scientists are training artificial intelligence to read the stars for us. These algorithms learn the patterns of chemistry and light, recognizing correlations too subtle for the human eye. They can identify atmospheric disequilibrium mixtures of gases that could only exist together if constantly renewed by life. Some systems are designed to hunt agnostic biosignatures, signals of living activity that don't rely on Earth's familiar molecules at all. Instead of asking, "Is there oxygen?" they ask, "Is this atmosphere trying to stay out of balance?" Because life, by its nature, disrupts equilibrium. A planet that refuses to rest chemically might be alive, even if it breathes something stranger than air. New technologies will soon allow us to watch those restless worlds in real time. Observatories will monitor how their atmospheres change over hours and days, tracking daily cycles of cloud formation, heat flow, perhaps even the equivalent of seasons. On Earth, the global concentration of carbon dioxide dips as forests grow and rises as they decay. If a similar rhythm appears in the light from a far-off planet, we may one day watch the heartbeat of another biosphere. We might see alien dawns and dusks written in chemistry. The search will not stop at biology. With every improvement in sensitivity, telescopes inch closer to detecting technosignatures, the atmospheric residues of civilization. Industrial activity leaves behind gases like nitrogen dioxide and chlorofluorocarbons, molecules that nature rarely produces on her own. The faint glow of artificial lighting on a planet's night side might betray cities. Radio telescopes, tuned to the frequencies of logic rather than nature, will listen for narrowband signals too precise to be random. The search for intelligence will become an extension of planetary science, not an outlier. Every new exoplanet studied will be checked quietly for the telltale murmur of thought. In this unfolding effort, Webb is the beginning, not the end. Its coronagraph has already shown what precision can do, dimming a star's brilliance enough to reveal the faint light of a smaller world. Future versions will go further, using adaptive optics to correct distortions instantly, shaping starlight so finely that even Earth-sized planets around sun-like stars will come into view. New spectrographs will peel atmospheres apart into their molecular components, each line in the spectrum a word in an alien language. The data will be immense, yet within that flood will lie the stories of origins, climates, and perhaps consciousness. What once felt like speculation is rapidly turning into cartography. We are beginning the first map of living worlds, a census of biospheres scattered through the galactic neighborhood. Within a century, the faint dots of today's exoplanet catalogs may become richly annotated, chemical profiles, climate models, perhaps even glimpses of color. Some entries will show worlds where life hums quietly under thick clouds. Others will display traces of technology, or atmospheres in transition, or eerie stillness. Each point of light will have character. The deeper truth behind these discoveries is philosophical. For the first time in history, we can test whether life is a local accident or a cosmic habit. The answer no longer depends on myth or metaphor. It will come from photons, from spectra, from the simple question, what is in the air of other worlds? If oxygen and methane share the same sky elsewhere, if carbon cycles flow on planets light years away, then biology is not rare. It is the rule. Perhaps the most beautiful irony is that our instruments are doing in light what life does in chemistry, seeking patterns, building complexity, reaching outward, Every mirror and sensor we send into the dark is another sense organ for a species learning to see itself reflected in the universe. The CE Antlier planet, faint as it is, reminds us that even whispers carry meaning if we learn how to listen. And the observatories now rising will turn that listening into something deeper, a cosmic census, a recognition of kinship written not in words, but in spectra and warmth and the fragile glow of worlds that, like ours, may be looking back. Sometime within the next 20 years, the night sky will look different, not in color or brightness, but in meaning. Dotted among the familiar stars will be small annotations in our minds, world with breath. Each one will carry its own chemistry, its own evolutionary story, its own way for water, carbon, light, and time to weave together. As that list grows, the universe will stop feeling merely habitable. It will begin to feel alive, rich, teeming, and endlessly inventive, its living processes unfolding on scales that make Earth's history seem almost modest. The great question, are we alone? They will lose its suspense. The answer, quiet but certain, will be no. And then comes the realization that the cosmos has always been crowded with company. That moment will not arrive with trumpets. Somewhere, in a softly lit laboratory, a scientist will sit before a computer and notice a small irregularity in the data from a telescope orbiting 1 million miles from Earth. The pattern of light will be unmistakable, a set of molecular fingerprints that could not persist without the hand of biology. No speculation, no wishful thinking, just the clean geometry of evidence. A line will be drawn, a note entered into the record. Humanity's long loneliness will dissolve, silently, like frost in sunlight. The doorway is already open. Inside the hydrogen clouds of K218b, warmed to about 120 degrees Fahrenheit, Webb has glimpsed an atmosphere in chemical disequilibrium, a trait found only on worlds where life is at work. Dimethyl sulfide, methane, water vapor, all dancing in patterns that make sense only if something is breathing there. The data carry a statistical confidence of 99.7%, enough to call it real by any scientific standard. We have not yet seen the organisms, but we have seen their pulse. Still, absolute certainty will come only when other instruments see the same thing, other telescopes, other wavelengths, confirming again and again until all alternative explanations fade. Random noise, instrument error, exotic chemistry, each ruled out with mathematical precision. Confidence will climb from 99.7 to 99.99, and then to the threshold where doubt becomes almost impolite. When that happens, the ripples will reach everywhere. Science will stretch outward to include biology as a cosmic principle, not a local accident. Philosophy and faith will change tone, adjusting to a universe that grows its own souls by the trillion. Technology will accelerate, tuned to new goals, observing, communicating, protecting, and deep within us, a quiet understanding will form the realization that the sky is not a ceiling above us, but a network of homes, each alive in its own way. Yet wonder brings responsibility. If the heavens are crowded with living worlds, our steps, whether spacecraft, radio signals, or mining ambitions, must become gentler. We will need new ethics for a living cosmos. How to explore without disturbing, how to share without overrunning, How to be neighbors in the truest sense. These will not be rules imposed by fear, but courtesies born of respect. From that moment on, history changes key. Humanity will stop being the species that wonders and become the civilization that knows. The universe will no longer be a void sprinkled with rare sparks of life. It will reveal itself as a grand ecosystem, a network of experiments in evolution, each world composing its own verse in the same vast poem. Looking back, we'll see that the spectral lines of K218b were not an ending, but an invitation, the first ticket from isolation to citizenship among the stars. Those fingerprints of alien air, gathered from 120 light years away, will be remembered as the evidence that ended our solitude. Children will one day learn about it the way they now learn about the first flight or the first step on the moon. That, their teachers will say, was the day we realized the universe had always been alive. And the discoveries won't stop. There will be worlds with oxygen and worlds with methane, worlds warm under greenhouse skies and worlds glowing from inner heat, worlds hidden beneath ice and others adrift in thick, luminous atmospheres. Each will offer a new answer to the same old question: what does it mean to live? Each will pronounce the word life in a slightly different accent. From the glowing dust rings of young stars like Ce Antliae, where planets are still sculpting order from chaos, to the ancient red dwarfs that will burn steadily for trillions of years. The stage for life is everywhere. The universe, it seems, prefers diversity over repetition. It doesn't make copies of Earth, it writes variations on a theme. That realization won't make us smaller, it will make us belong. The next generation of observatories will make the picture sharper still. Improved coronagraphs and wavefront correction will let telescopes see an Earth beside a Sunday. Spectrographs will read alien skies like books, line by line, molecule by molecule. Artificial intelligence will find the faint seasonal rhythms, clouds forming, gases rising and falling that mark the metabolism of entire worlds. And perhaps, someday, a faint point of artificial light will blink on the night side of a distant planet, or a thin trace of industrial gas will whisper through its air a sign of thought, a quiet knock on the glass from the other side. Even so, the most moving part may not be the technology, but the feeling. For the first time, we'll sense that the cosmos is not a stage, but a neighborhood. We'll imagine standing at the edge of an alien sea and knowing someone, somewhere, might be standing at theirs, looking up at the same stars. The children born after that discovery will never know a universe that feels empty. To them, life everywhere will be a simple truth, like gravity or light. We'll learn to celebrate carefully. Not every living world will want our voice in its airwaves. Some will need distance, a respectful silence. Others might answer in their own strange language, a chemical rhythm, a flicker of light, or a deliberate quiet that says, "We hear you." In such a galaxy, courtesy will become the new science. To listen without taking, to approach without crowding, to learn without claiming. And through it all, James Webb will remain like a golden ear in the dark, still listening, still patient, still finding whispers hidden in the shine of stars. Around it, new instruments on Earth and in space will join the chorus. The music has already begun, soft, even, steady. When the final certainty arrives, it won't come with fireworks. It will come on an ordinary afternoon in a room filled with coffee cups and code. Someone will exhale, type a note in the margin of a dataset, cross-checked independently, signal confirmed. The numbers themselves won't change the world, but the story they tell will. We will start dreaming not as a lonely species, but as residents of a breathing universe. Close your eyes for a moment and imagine it. Skies of crimson, indigo, and pale gold, inhaling and exhaling through invisible lungs. Somewhere, children are asking their own version of our oldest question: is there anyone out there? And their elders are smiling, saying, yes. And somewhere out there, you are there anyone. We were never truly alone. The universe has been alive all along, waiting for us to learn how to listen. Even now, in the quiet between stars, you can almost hear it, the slow, steady rhythm of worlds breathing together, and us, at last, breathing with them.